best seats in the house. Well, good evening, and welcome. It's good to see so many familiar faces, and it's equally as good to see so many new faces here tonight. That's what we are trying to do, is increase our numbers as we go along. By way of introduction, I'm Dave Cook. I'm one of the directors of NewSpace Chicago. And my day job is I'm CEO of a startup called Hurst Chicago. Hurst Chicago is what we refer to here at NewSpace Chicago, and I bet you I mixed those two up before I've done it. Hurst Chicago is what we call a space-scalable business. Space-scalable business just means that it's a business that can be started here in a terrestrial, if you will, market, but be expanded over time into a space-based business to use the resources of space to make money. That's why I got involved here when I heard Dave talk at a Chicago Society for Space Studies meeting a couple of years ago. Dave started talking about space-scalable businesses, and the light bulb went off in my head. Hey, that's what Hurst Chicago is. So I've been involved here for a couple of years. If you're thinking about becoming more involved with us because you want to start a space business, or you want to work for a space business or advise a space business, I can tell you just briefly how it's worked for me so far. Over the last couple of years, I've been able to recruit 3 people to our leadership team for Hurst Chicago from NewSpace Chicago here. Recruited an investor, Dave. He's one of our founders. He has a founder jet card, Hurst Chicago. And I've also met people who have been working with us to connect us to money. We've raised funding one round through a crowdfunding offering through a person that we met here, who was a speaker here one evening, and we're about to launch our second crowdfunding offering in a week or so. So NewSpace Chicago has been very, very helpful to me in getting Hurst Chicago going. So again, if you're an entrepreneur, want to be involved, this is a good place to get that going. Well, a couple of announcements I'd like to make, or requests, if you will, before we get going with the presentation. We're always looking for more volunteers. As I'm sure you can appreciate, there's a lot of work to do here to get an organization like NewSpace Chicago going. Even though we've had it about 3 years now, there's still work to do, a lot of work to do to expand our numbers. We have committees. We're looking for more committee members. We're looking for people who want to be on the advisory board. We're looking for new members who want to expand our board of directors. So if you have an interest in getting more involved, please let us know before we get out of here this evening. We'll be happy to talk to you more about it. Also, I'm sure you noticed we asked for a donation when we came in. It's just us chickens. We don't have a sugar daddy behind the organization, so we're always looking for help funding what we're doing. And you'll hear more throughout the year if you get on our mailing list of all of the things that we're doing. Well, I think anything else, Dave? Let's get to the main program. That's what you came here for today, to find out about Nanosatellites. Dave is great. Our oldest sponsor. I'm sorry. Now this is the big challenge. Technology, huh? They want me to put all my personality and my brain into the singularity and live on the internet, right? I don't know. Dave's queuing that up. There we go. We have 2 regular sponsors that support what we're doing. MHub, of course, is the building where we're at here, and we're doing a lot of interesting things with them. We're talking to them about putting together an incubator for space businesses here. That's coming along. And Metropolitan Brewing has donated all that good beer that you're drinking tonight. One more, did you? So, without further ado, let me introduce Dave. Again, I met him only about 2 years ago, but I've been really impressed with his leadership and his drive, enthusiasm for establishing here in Chicago a center of excellence for commercial space development. Dave's been an entrepreneur for many, many years. He has several successful tech startups under his belt. His professional skill, if you will, is a software engineer. So he understands how those bits and bytes work. He founded Orbital Transports that is in the business of creating an infrastructure for entrepreneurs who want to go up there and do things in lower orbit. We really have been talking on and off about nanosatellites, I think, since we started, right? But I don't recall having a really good briefing on what's going on. And that's what Dave is going to do for us tonight. So without further ado, Dave Hurst.
Thanks, Dave. So, as Dave mentioned, I'm going to talk to you about what's going on in the nanosatellite industry. But before I get into that, I want to veer off topic a little bit and ask if anybody is aware of the incident that happened last week on the space station. Good. It's good to see you guys are tracking it, where they observed that the pressure in the space station was dropping due to a puncture in the Soyuz spacecraft docked to it. This is of interest to orbital transports because we're developing a system to detect micrometeorite impacts on structures like the space station. And I was curious to find out what actually happened. It turned out it's nothing so interesting. It was a mundane manufacturing error by some technician in Russia who drilled a hole and then covered it up, literally and figuratively. But it's just interesting to see these things happen, and they are real, and there's definitely a need for it. And I'm glad to see that so many of you are actually tracking what's going on in space, so that's good to know. So this evening, I'm going to talk about nanosatellites and where the industry is going. So about a month ago, we attended a conference called Small Satellite. This is in a small town in Utah called Logan. It's about 70 miles northwest of Salt Lake City. And this is the premier event if you have any interest in small satellites. Now, I'm going to use the term small satellites and nanosatellites a little bit interchangeably. They actually mean different things, but in this context, for what we're talking about tonight, let's say they mean the same thing. This conference was attended by over 3,000 people, and there were over 200 commercial exhibits, over 150 presentations in the sessions, and over 70 posters presented. This represents an amazing amount of activity in the small satellite industry. That number of attendees was more than has ever been to this conference in the past. And so a lot of what I'm going to be talking about tonight comes from things that I saw at that conference. Of course, this will also include information that is just from my research of the nanosatellite industry in general. So nanosatellites have been a revolution in the satellite industry. They're cost effective, they can be delivered very rapidly, the technology is improving tremendously, very quickly, and they are using commercial off-the-shelf components. And so this provides access to space to organizations that did not necessarily have the ability to go to space before. And so this has sparked tremendous activity in this satellite industry, focusing on nanosatellites. And so there's a huge need for outsourcing and companies who can deliver on nanosatellite missions. So here's a graph showing some of the growth in the industry over the last 5 years or so. In 2017, there were over 300 satellites launched into space. Nanosatellites launched into space. And according to SpaceWorks, it's projected that there will be somewhere on the range of 250 to possibly over 400 launched next year, and similar growth the following year. You'll notice, by the way, this this dip right here in 2016 is very interesting. That was a result of the SpaceX Falcon 9 incident that happened on the pad toward the end of 2016 when the rocket blew up. There were a whole bunch of nanosatellites that were either on that mission, on that launch, or were queued up to go. And so those missions actually were delayed into 2017. So that's why we see there's a little bump here, but this trend is going up. And SpaceWorks estimates that over the next 5 years, there's going to be over 2,600 nanosatellites launched into space. So this represents tremendous activity and tremendous growth in the sector. So small sat operators, broken down into several different categories here: academic, commercial, government, civil, government, military, and nonprofit. Notice up here at the top, these are the academic nanosatellite missions. And those are of interest because nanosatellites, as I'll mention in a minute, actually came out of university programs. And so the really amazing thing is to see the growth in the non-academic sectors. In particular, the growth in the commercial sector has been just tremendous. And you can see that reflected here. Those numbers are a little bit deceiving because when you break down the commercial operators, it turns out that 2 companies are responsible for the majority of those satellites that have been launched: Planet and Spire Global. Those 2 companies are operating large constellations of nanosatellites. And so it's interesting to observe how much one company can actually skew the statistics for the entire industry. Nonetheless, this still represents a lot of activity, and the constellations have been launched, and so although they will need to be refreshed over time, the upcoming launches are actually going to be not just those 2 companies, but a number of other companies as well. The constellation operators are actually going to be a significant portion of that, and we'll see some examples of that as I move on. Okay, so I'm talking about nanosatellites. I'm sure at this point some of you are asking, so what is a nanosatellite? Really? I mean, nanosatellite? What does that mean? Okay, so a nanosatellite, by definition, is a satellite that weighs between 1 and 10 kilograms. So that's not very big. When we start talking about small satellites, that limit goes up a little bit higher. You get into the 10 to 100 kilogram range. So again, there is some overlap between that. And when I talk about small satellites tonight, or nanosatellites, I'm basically talking about that same range. These are not nanosatellites. What we're looking at here is the GOES satellites, GOES 16 and GOES 17. They are operated by NOAA, and they are basically geosynchronous Earth observation satellites that will be collecting weather data. As you can see, they are quite large. This one here on the left, this is GOES 16, it's about 20 meters tall. So these things are enormous, and sometimes it just boggles my mind to think about that something that large being put at the top of a rocket and thrown into space. But they do that all the time. Here's another example. This is the NASA mission to measure the magnetosphere. And what we're actually looking at here are 4 separate satellites. Each one of these is 4 meters high and about 10 meters in diameter. So that's 4 satellites stacked on top of each other. Again, these are not nanosatellites. This is a nanosatellite. Compare that. This is 10 centimeters on the side. So it is a cube that you can fit in the palm of your hand. And the interesting thing is that the technology has been improving so much in the last 10 years or so that the amount of functionality that you can put into a 10 centimeter cube is just amazing. And let me give you an example. Think about what goes into this. There's a lot of functionality in this cell phone. You have a camera, you have Wi-Fi, you have cellular, you have a screen, you have a supercomputer that will blow anything from the 1970s out of the water, and it fits in your pocket. That's amazing. Okay, so that's half a centimeter thick. So you can imagine stacking several of those up into a 10 by 10 by 10 cube. So there's a lot of functionality that we can put into that space. As I mentioned before, nanosatellites were originally part of university programs. A gentleman by the name of Bob Twiggs at Cal Poly in San Luis Obispo came up with this standard for satellites that university students could work on. And so it gave them the opportunity to build real satellite technology, make something that would work and something that would fly in space. But the brilliant innovation was that he made it the standard. He said, everything has to fit into this 10 by 10 by 10 cube, and that will be a standard size. And so with that standard, we can have a standard deployer. And the advantage of the standard deployer is that integrating the satellite into the launch vehicle becomes very easy. The satellite manufacturer, the satellite builder, the people who are making the satellites, all they have to do is fit to that particular interface spec. And then we put it into this P-pod deployer. In this case, the deployer will actually fit 3 10 by 10 by 10 cubes. And it goes in there, and it fits on these rails here, these rails, and there's a spring. And when the door on the P-pod opens, the spring pushes the satellite up. It goes into space, like that. So here we see a CubeSat, 10 by 10 by 10 cube, being launched out of the P-pod deployer from the space station. Easy, real easy to do. And so that innovation opened up enormous possibilities for lots of people to get into the space business. And so the nanosatellite revolution was born. Now that was about 15 years ago, so we've had some time for things to develop since then. One of the things that's happened is we discovered that, okay, a 10 by 10 by 10 cube is nice. We can do some interesting things with that, but we'd like some more space than that. And so they developed some larger form factors. So 2U and 3U became very popular. You basically put 2 or 3 cubes together and you have more space. And more recently, the 6U and the 12U are starting to become popular as well. But most of the images that you're going to see tonight are going to be of 3U satellites. So that's the very popular form factor right now. But the 12, and the 6 and the 12 are becoming more popular as we go along. So how do we get these things into space? We put the cube into the P-pod deployer. What does that go on? Well, that goes onto a rocket. This was the second innovation in the nanosatellite business, which is that if you're going to put a geosynchronous communication satellite into space, you're going to fit it on the top of an Atlas V or a Falcon 9, and you're going to take that entire rocket. You're going to put your satellite into space on that rocket launch. Well, you're not actually going to take the entire rocket. What you're going to do is use most of that launch capability, but there's going to be some excess launch capacity. And so what they do is that excess launch capacity can be devoted to rideshare, secondary payloads. So once the primary satellite gets launched to its destination, the secondary payloads then get deployed. And so this provided an opportunity for universities and other people to put satellites into space as long as they could go somewhere where a satellite was going. So this graph here shows the number of different launches on different launch vehicles that had nanosatellites. The really interesting thing here is, okay, Atlas V, that's the legacy launch system. That's been launching a lot of them. And Falcon 9, of course, this is SpaceX. Everybody knows SpaceX. But what's fascinating is that in 2017, the organization that launched the most CubeSats was actually the India Space Research Organization. That's PSLV, Polar Satellite Launch Vehicle. So India is getting into the nanosatellite business in a big way. And we expect to see a lot more nanosatellites being launched by Indian rockets. That's a really interesting development. So, okay, we put our nanosatellites on a rocket, and then what? This is an example of a rideshare. Spaceflight Industries is a company that basically buys up launch capacity and then resells it for small satellites. And they've developed something called the Sherpa, which is this ring device here. And so if you know how satellites are integrated with a rocket, there is an integration ring. The satellite fits on that, and that ring is connected to the upper stage of the rocket. So when they release the satellite, that ring releases the satellite. So what spaceflight did was they put that ring on top of this little device called Sherpa and put a bunch of nanosatellite deployers on the ring. So this gives them the capability to launch a whole bunch of nanosatellites all at once. They send up the rocket, primary payload goes, then the Sherpa deploys and shoots all the nanosatellites into space. So this is an example of rideshare. But there are other ways to get your nanosatellite into space as well. You can deploy from the ISS. So here we see the NanoRacks CubeSat deployer. This device right here contains some P-pods, and the Canadarm on the space station pulls that thing out of an airlock and points it basically in the wake of the space station, so they're going the other way from the space station. And then they pop them out into space. So if you want to put your nanosatellite into an ISS orbit, this is a great way to get into space. Your nanosatellite will ride up to the space station on a Dragon capsule or a Cygnus capsule. The astronauts will take the deployer through the space station into the Kibo airlock, the Japanese module, and put it outside. The Canadarm will pick the thing up, point it in the right direction, and shoot your satellites into space. The advantage here is that it's less expensive than buying your own rocket, or buying your own part of a rocket. But there are a whole bunch of new launch devices, launch vehicles that are being developed. These are dedicated small sat launchers. The most well-known, or the most advanced, I should say, is Rocket Lab. And they had a successful test of the Electron rocket earlier this year. They deployed 3 commercial CubeSats, 3 new CubeSats, into polar orbit. So it's very good to see these commercial launchers starting to fly. The advantage of a rocket like this is that you can put your CubeSat, your nanosatellite, into the specific orbit that you want. You're no longer tied to the orbit that a primary payload is going on. You put your satellite into this launcher, and it goes where you want it to go. So it turns out, in 2017, there were 34 companies who were developing small satellite launch vehicles. That's enormous innovation. 34 launchers. If you think about the incumbents in the launch industry right now, you're talking about SpaceX, ULA, India Space Resources Organization, Russia, and that's about it. So 34 new launchers is a lot of innovation happening. And the interesting thing is that they're looking at a lot of different ways of launching. So in this column here, you see land, sea, and air. So that means the rocket is being launched either from a pad on the ground, or it's being launched from a boat at sea, or it's being launched from a plane in the air. And we're not going to actually get into some details of that, but it's interesting to see all of this innovation that's happening. I want to look at a couple of these. I realize it's hard to see all of these, but let's look at a couple of them. One is Firefly Aerospace. It's really good to see these guys back in operation. They were suspending operations about 2 years ago, basically because they ran out of money. And they were pretty far along in their operation. So it's good to see them back in operation again. They got funding, and hopefully we'll see them flying next year. Okay, here's another one. ISRO. So we talked about the Polar Satellite Launch Vehicle before. ISRO is developing a small satellite version of that, the PSLV flight. So again, India is getting into launching satellites, small satellites, in a really big way. Down here toward the bottom, Stofield Aerospace. Those of you who were here earlier in the year may remember Stofield Aerospace, because Brian Stofield came here and presented to NewSpace Chicago. So it's interesting to see they're getting a little bit of traction here, and nice to see them in this list. Finally, down at the bottom, Virgin Orbit. This is the one that gets all the press. Richard Branson's company, Virgin Galactic, was talking about sending people to space. They've been working on that for the last 15 years. It's been taking them a long time to scale up from Spaceship 1 to Spaceship 2. But the interesting thing is that they have spun out from that technology Launcher 1. And this, again, is an air-launched rocket. So like Spaceship 1 and Spaceship 2, the space vehicle is attached to an aircraft. The aircraft goes up to about 30,000 feet, and then they launch the spacecraft from there. In the case of Virgin Galactic, it's a spacecraft that carries people. They go into space, they come back down. It's a suborbital flight. But in the case of Virgin Orbit and Launcher 1, it's a rocket, and that rocket goes to space and it puts your payload into orbit where you want. So again, a lot of really interesting innovations in how to get things into space. The other aspect of this is cost. So this graph shows two things. The blue dots show the cost of a launch in millions of dollars. And most of them are less than $10 million per launch. There are a couple that are more expensive than that. So we've got one at $17 million and one at about $32 million. As launches go, that's cheap. But the really interesting number is not the cost of the launch, it's the cost per payload, cost per kilogram to orbit. And what's interesting here is that the cost per kilogram for these specific launchers is high. We're talking typically $15,000 to $30,000 per kilogram, and even as high as $68,000 per kilogram. That's very expensive. And by comparison, if you're going to put a payload into space on a Falcon 9, it will cost you somewhere in the range of $2,700 per kilogram. Now, the difference is that on a Falcon 9, you're going to be launching a lot more than a few kilograms into space. Those, again, are the big payloads. So the trade-off here is flexibility and convenience. Excuse me, flexibility and convenience versus cost. So if you want to go to a specific location and you want to get there now, these guys will do it for you, but it's going to cost you. If you don't care how you get into space or where you go as a rideshare. So again, it's interesting to see how this industry is playing out and the innovation that's happening and really the development that's happening there. Okay, so we've talked about nanosatellites. What are they? We've talked about how do we get them into space. The next question is, what do you do with a nanosatellite? So there are basically 5 different applications. Earth observation, remote sensing. That's the obvious one. What's going on the ground, we want to see it from space. Second one is communications. And there's a lot of interest in developing internet connectivity as well as narrowband communications from satellite constellations. The third one is science experiments. We want to do something in zero gravity, we want to do something in a vacuum environment, put it on a satellite, launch it into space. The fourth application is technology demonstration. And here we see people who are developing technologies of one kind or another that need to be qualified in space. So again, you put that on your nanosatellite, launch it into space. The fifth one is kind of a catch-all, novel applications. So there are a lot of different things, but they tend to be one-offs that are going on. So here's some examples. In the Earth observation, this is a mission called HED-1. It's a Chinese company, HED Aerospace. And their application is tracking ships at sea using the Autonomous Identification System, AIS. Ships use that to identify what they are and what they're doing. So here we see HED-1, it's the first satellite, but this is the first one of a planned constellation of over 30 satellites. And this launched last November. Okay, here's an example of a communications application. This is 3 diamonds, because there's 3 of them. And this is a narrowband communications application. Again, they are building a constellation. Ultimately, they want to have 200 of these things in low Earth orbit, providing communications in more or less the equatorial space. And the 3 diamonds launched in June of last year. Okay, here's an example of a science application. This one is really cool. I actually had this idea, and I saw that somebody had done it already. So, Space Pharma is building a micro laboratory that fit in a 3U CubeSat that they can do biotechnology, biochemistry, microbiology experiments in a zero-G environment. So there's a lot of kinds of things that you can do with that. For example, growing protein crystals in microgravity. It turns out you can grow better crystals in microgravity than you can on the ground. So that's one example. They're also experimenting with different things regarding bacteria and other microflora. So this is an opportunity to put biological experiments in space on a CubeSat. This one launched, the first experiment launched in February of last year. Technology demonstrations. So DSAT from D-Orbital is a de-orbiting device. Basically, it's a propulsion unit. You fire it in the opposite direction that you're going and bring the CubeSat, your small satellite down. This was launched last year in June, and the actual DSAT mission had some other things associated with it, but this is an example of a technology demonstration. You need to qualify in space. Once it's been qualified, then it can be used on a variety of different missions. Okay, here's the weird one. This is the Amaya Satellite. It's from some students at Moscow State University of Mechanical Engineering, launched in July of last year. They wanted to put the brightest object in the sky in space. So they basically built a tetrahedral-shaped reflector, which unfolds from a 3D CubeSat. And it's very shiny, and so when it's flying overhead, it's in sunlight, you're going to see it from the ground. It'll be very bright. The point of this mission, I think, was to say, hey, you put something in space, but the technology was also being used to test another de-orbital device. In this case, the drag from the large reflector would cause the satellite to come down over time. So those are some of the interesting missions that have been happening. Now I want to talk about some of the things that I saw at the SmallSat conference. First one here is a device called Magtag. This is an interface for servicing satellites. You can think of it as a USB connector for your satellite. It connects magnetically, it couples with a magnetic field, and it's designed to not radiate magnetic field outside of the coupling. So it's intended to not interfere with your electronics or EM or other things like that. But basically it allows you to snap together components to a satellite either before it's launched or, more importantly, after it's launched. And so using this, you can rendezvous with the satellite, upgrade a component, and it just connects because it snaps together magnetically. I actually got a chance to play with the prototype of this device at SmallSat, and it's very impressive. The magnetic coupling is strong. You could not pull it apart just by strength alone. You had to turn it off in order to separate the pieces. But the interesting aspect here is this component right here. Now, for this prototype, they had a particular connector, which is a coax and some other stuff there. But you could put any kind of connector that you want in there. So electrical components, communication connectors, and also, very importantly, fluid couplings for refueling satellites. So I expect to see some interesting things from Althea's space machines. regarding satellite servicing with this technology. So you might have heard that NanoRacks is putting a commercial airlock on the space station. I was kind of curious what that really means. And so NanoRacks presented some information about the Bishop airlock. This is computer graphics, but it's showing the Bishop airlock here connected to I believe it's node 2. It's the same module on the space station that has the cupola. And you look at that and it's like, that's an airlock? Really? What's going on there? So it doesn't actually open the way you would expect an airlock to open. Here's what's going on. This is a bell jar. And it connects to the docking adapter on the module. And it provides opportunities inside here for putting experiments and other things, either inside. It also has connectors on the outside to have different experiments and so forth connected to it. Here's another view. You can see they've attached some small satellites and so forth inside the bell jar. So how does this thing work? This is a really fascinating thing. So that's connected to the space station. The astronauts open up the docking port on the module. They put the small sats or whatever inside. Then they close it and take it off. So the Canadarm connects to this thing here and pulls it off the space station. And then it can be aimed in any direction that you like to release your satellites into space. So this represents an order of magnitude in capability for releasing nanosatellites into space. You can point them in any direction that you like. And interestingly, if you orient that so that the back of the bell jar is in the RAM direction, that's the direction of travel, so that the open part is facing behind you, you actually have a very clean vacuum environment. So as the space station is traveling through space, it's not actually out of the atmosphere. You're in a very thin environment, but there are particles and other things there. But by having the bell jar going through space with the opening facing the back direction, you avoid all of those things. And so you have a very clean vacuum environment, which provides an opportunity for a variety of vacuum experiments. Anyway, it's a very interesting capability. I'd be very, very curious to see what they end up doing with that as things go on. Oh, Orbital Transport's had a booth at SmallSat. This is our booth, and the takeaway from SmallSat was that there's a tremendous amount of interest and activity in this industry. Everybody that I talked to said that they had a great conference. There were all kinds of opportunities happening. My company came home with numerous leads, and it's just a testament to the amount of activity that's happening in this in this industry. So with that, I'd be happy to address any questions that anyone has. So Brendan's going to grab the microphone.
I can just shout. How much does a CubeSat cost?
So it depends. And it depends on a couple of different things. One is what kind of functionality you want. So if you want to put together a 1U CubeSat that basically transmits a beam signal, they call it a beamsat, you can probably do that for $20,000 or $30,000, exclusive of launch costs. If you want to build a satellite that's actually going to do something, maybe you're going to have attitude determination control, you want to point, say, at the ground and take photos of what you want to take photos of, then you're going to be spending a lot more money. So typically when I'm talking to a customer and they ask me, so how much am I going to spend on a nanosatellite mission? The answer is think about $250,000 and up from there, and plus a launch cost on top of that. And there are a variety of approaches to getting launches. So if, for example, you're an educational institution, there are programs where NASA will launch your CubeSat for free. But typically you're talking about somewhere in that range.
When does the number of these things get so large that control is lost and they become space hazards?
So that is a question particularly when we're talking about constellations. And so I mentioned one of the satellite operators is going to put 200 satellites in space, and there are also proposals for thousands of satellites in a constellation. I think one of them is talking about 4,000 satellites. Two aspects. One, space is big. I mean, space is really big. And so there's going to be a lot of space between the satellites. But on the other hand, it is a concern because there have been collisions between satellites, and when that happens, it generates more debris, and that just increases the problem. So as to when that would become a significant issue, it's something we have to pay attention to now. But I don't see it as becoming a huge hazard for a number of years yet.
How many of the satellites that are placed in orbit or semi-orbit actually come down to Earth, or how long is their life in the orbit?
The typical lifetime, it depends on the orbit that you're in. Satellite in low Earth orbit, say 400 kilometers up, typically last maybe 18 months to 2 years. You go a little bit higher than that, 500 to 600 kilometers, you're probably talking 2 to 3 years. You get further out than that, then it'll be a while. And then deorbiting actually becomes a significant issue. And there are regulations that you're required to deal with in terms of the end of life of the satellite. So you actually have to make a plan for when your satellite is going to be deorbited, if it's not going to come down just naturally.
And you showed the graph where you showed India is really leading in terms of launches. What are their plans for the satellites? How are they going to utilize it? Any idea?
So they're basically doing commercial launches. The question was, what is India doing with all of the launches that they're doing? And the answer is that they're selling launches to people who want to put things in space. So, for example, I think it was last year, Planet, which is currently operating one of the largest constellations, put 88 satellites into space on one launch. And it was done using the ISRO launch vehicle. So they're basically providing launch services to commercial customers.
Thank you for the presentation. You had just mentioned Planet.com, and in a sense, if you use their web service, you're renting in a sense. Is there any companies that are putting nanosatellite up but renting those out?
So
Or
the
do we
question
not
is,
reach that?
are there any companies that are renting out capacity from nanosatellites?
It's already been launched.
Right. So there's a couple of answers to that. One is, if you're talking about a geocommunication satellite, yeah, they rent capacity on those kinds of things all the time. As far as nanosatellites go, Planet, which you mentioned, is not actually renting services. They're just downloading the data and then selling the data. Right. So there are other examples. So, for example, the space pharma that I mentioned, that's basically what they're doing. It's launching a capability into space and then renting that to customers. So I don't think we're seeing any of that kind of thing right now, but it's definitely coming.
Thanks. A couple technical questions. How do you get power on these things? 10 centimeter by 10 centimeter, even if you cover it with solar panels, if you're in Leo, you're shadowed, a good part of the day. How do you get enough power to do anything.
So if you remember the image of the 10 centimeter CubeSat, it was covered with solar cells. It's going to collect power when it's in sunlight. When it's in eclipse, it's not. So it's got to run on battery power. But that's really a matter of how much power the satellite itself is drawing. So for a deep set, you're not going to use much power. But if you want to do more sophisticated capabilities, then it's going to use more power. That's one of the reasons why you might go to a larger form factor. So one of the things that we didn't see here was there are, in particular, 3U CubeSats have deployable solar cell panels. So they look like they have wings, basically. So once it launches, then the panels unfold, and that gives you more square footage to collect solar power.
Yeah, that makes sense. As you're going to those 2Us and 3Us, the volume of the things increases faster than the surface area, so you really have to start deploying.
Yeah, that's right.
So the other thing is attitude control. Are there little reaction wheels inside these things, or what? How's the attitude done?
So attitude control can be done in a couple of different ways. You mentioned reaction wheels. Yes, that's a common approach. There's also a technology called a magneto-torquer, which interacts with your Earth's magnetic field. And so you have basically a magnetic coil. Actually, you have 3 magnetic coils aligned in 3 directions. They can be used to orient the satellite. That, of course, requires power. And then there are also some electric thrusters, basically plasma thrusters or Hall effect thrusters that can be used for attitude control as well. Again, that uses power also. But yeah, there are several different ways for attitude control.
Are there any government regulations yet in this industry?
I'm sorry.
Are there any government regulations or restrictions in this industry so far?
Yes.
Any bad?
So there are a number of different regulatory regimes. The most obvious one is the FCC for communications. You need to license your communications. And that takes some time and also some money. Other regulatory regimes, if you are going to take images of the Earth, actually if you're going to put a camera into space, whether you're going to look at the ground or not, you have to get a license from NOAA. And then there are various other regimes that you have to deal with as well. So you've given me an opportunity to plug next month's event with my friend Charles Mudd, who will be talking about space law and some of those issues next month.
You mentioned that they were $250,000. Who makes the satellites? Does each launch or each operator make their own satellite, or are there satellite producers that have sell based on their performance?
So there are a number of companies that produce various components for spacecraft. So the big 5 are NewSpace. They're probably the most well-known. ISI Space, Vulcan, Clyde Space, and I believe the 5th one is Endurosat. So they make the CubeSat structure and various of the components like communications and onboard computer. They will also make things like ADCS. Then there are a number of other manufacturers as well. For example, Berlin Space Technologies makes ADCS modules.
What is ADCS?
Attitude Determination Control System. There are other providers who make propulsion systems. So, for example, Tesseract Space, they have a green propellant propulsion system. Phase 4 makes an electric propulsion system. There are a number of propulsion providers as well. And so there are quite a few manufacturers that make the different components. So you can go to a provider like NewSpace and say, hey, build me a thing, and they'll do it. Then there are also providers who will do an entire mission for you. So, for example, my company, Orbital Transports, will do a complete mission for for a customer. We'll talk to you about what your mission objectives are. The systems engineering will design the vehicle, integrate it, make sure it gets tested properly, find a flight opportunity, put it in space, and get your data back to you. So there are a whole ecosystem of companies who can help you get yourself in space.
Thanks.
Thanks a lot for the talk. I'd be curious to hear your thoughts on the recent interest of Facebook or Google's on satellite connectivity. Facebook dropping their drone program and a month later investing massively or changing priority and putting a lot of effort on their satellite deployment. Do you think it's going to change the industry a lot? Any thoughts you have on that?
So Facebook and Google have lots of money. They're trying to figure out what to do with it. And so they want to extend internet connectivity to the entire world so that they can sell ads to more people. So hence we're seeing proposals from Facebook and Google to create constellations of nanosatellites for communications in particular. I haven't actually seen a lot from those companies lately, so I'm not sure where those initiatives are. I'm seeing other companies that are kind of jumping into that space. OneWeb is probably the most well-known, but then there are others like the company that I mentioned earlier that's also intending to build a communication constellation for communications.
What are the largest costs in the development and deployment of these satellites, just outside of paying for your ride into orbit?
Yeah, so the costs break down more or less like this. Launch is a significant part of it. Hardware can be quite expensive, particularly when you take into account the fact that even if you're going to fly just one satellite, you probably want to build two of them. Because you want to have an engineering test model that you can work with on the ground. Well, your flight model is actually doing something, so if something goes wrong, you can try to replicate the problems. So hardware is going to be your second largest cost. And we were talking about ADCS components earlier. That will run you just for that piece alone somewhere in the range of $30,000 to $50,000. So hardware costs are definitely significant. The third major cost is going to be the man hours it takes to build one of these things, to design it, do the systems engineering, testing, and so forth. And so testing then becomes a significant part of that cost as well.
It sounds like it's probably going to take about 35,000 kilometers. I was wondering why we can't just send it to 30 kilometers, like the stratosphere. How is it going to
Sorry, I'm not hearing you very well.
see, usually the satellite already goes to 35,000 kilometers.
So a satellite at 35,000 kilometers would be a geosynchronous orbit.
Can we, is it possible to send something to 30 kilometers,
35 kilometers.
instead of 35, send it to 30? Yeah.
Oh, is that a specifically known orbit? 30 or 30,000? 30 kilometers?
Yeah.
It's not in space.
Right above the plane.
Yeah, 30 kilometers up is not in space. That's in the stratosphere.
But it is going to sustain, is it possible to sustain?
No, it's not in space, and that's in the atmosphere. So it'll come. If you try to get to orbital velocity at 30 kilometers, you'll burn up right away. If you wanted to go to 30 kilometers, I would suggest using a high altitude balloon.
That's what I was saying. Maybe that they transfer one meter.
No,
big of a problem is radiation, not something that's come out of the electronics?
Excuse me. So that's a very good question, actually. And the radiation environment varies depending on where you are. So in low Earth orbit, typically the radiation environment is not severe because you're below the Van Allen belts. And so you're kind of protected by the Earth's magnetic field at that altitude. Now you get much higher than that, and it's a whole different story. You go to geosynchronous, you're in the Van Allen belts, and you've got a hard radiation environment. So that does have a strong effect, actually, on what you can build. And so I talked about commercial off-the-shelf components earlier. We see a lot of CubeSats and other nanosatellites being built with basically off-the-shelf hardware. And in this case, I mean like consumer electronics grade off-the-shelf hardware, which is not rad hard. And so that actually contributes to significant failures in a lot of cases. That said, your chances of survival in low Earth orbit are going to be pretty good. You go somewhere else, it's a whole different story.
Can I add one thing there?
What's that?
Can I add one thing to that?
Yeah, sure.
So one of the things I saw in regards to the hardware that SpaceX uses on some of their equipment, they use a lot of off-the-shelf things, but they'll build in redundancies of the hardware to basically assume that if one of the devices got corrupted, the other two can kind of like cross-check. So even though the hardware itself is cheap, they kind of like try to get around it with certain redundancies. I'm not sure if that's used in like CubeSats, but like they're still using cheap components, but a lot of them to kind of like say, okay, well, if all of them fail, it's very unlikely, but one might fail, and we'll know that that might have gotten corrupted by radiations.
You know, when you're talking about radiation, there's basically two different issues that you have to deal with. One is what they call a single event, where a bit gets flipped by a cosmic ray or something like that, and that will cause program errors. The other case is where the radiation just degrades the electronics entirely. And so the first one, the single bit event, is more of an issue in low Earth orbit because the radiation environment is not that hard. So as Brendan was saying, redundancy helps a lot. In fact, just today I was reading an interesting paper on survivability of essentially consumer-grade electronics in space. And one of the approaches is when you have a system that detects an error, it just reboots. It powers off, powers on again. So that's one approach.
Is the ECC RAM used in space? Sorry. Is the ECC memory used in these components?
I want to say UCS RAM more than ECC memory.
Sorry.
What are the implications for narrowband types of communications with these satellites? Are there any that could be accessed as far as communications for what we're using technologically on Earth now?
So you're asking the opportunities for narrowband communications. Actually, I think they're quite significant. The company that I mentioned earlier that's doing the constellation for communications, they're actually planning on using narrowband communications. So yeah, I think there are significant opportunities there. Question over there.
It's been about 60 years since the first satellites went up secretly in the United States to photograph secret places in Russia. They didn't know it. And can anyone put up a satellite and take photographs in China and Russia? That's my question.
So, as I mentioned before, if you are in the United States and you put a camera on a satellite, you have to get licensed by NOAA. So they will ask you what your mission profile is and what you're going to take pictures of, obviously. Are they going to care if you take photos of China and Russia? Probably not. They're concerned about United States security. The Russians might have something to say about that. But So yes, there are regulations that you have to deal with, but if you're launching from the US, you don't really have to deal with Russian regulations. Now, there are international agreements that affect that as well. So I'm not sure about China or Russia, but I do know that there are significant restrictions on what you can photograph over Israel. Why Israel specifically, I'm not sure, but I know that there are those restrictions.
How do they even know you? Like they can't. So, and they can't lock down your satellite either. So, can they even track them?
Yeah, well, all of the satellites are tracked. So, in fact, there was a big flap recently about a company that was in stealth mode, and they tried to get a license from the FCC. The FCC denied their license because they were concerned about orbital debris, because this company was putting up not nanosatellites, but picosatellites. And the FCC was concerned that those would be difficult to track. So yeah, pretty much everything that goes up gets tracked. There are public databases of all satellites that you can just go and look at the databases. Okay, the black satellites are probably not in those databases, but aside from that. But the point is that if you're putting something into space, it's got to go through a launch provider, and so they're going to do a due diligence on that. Other questions?
So in that regulatory scenario, who's the they?
Who's the they? So NOAA.
That's if you're going from the U.S.
I'm sorry?
There are lots of other places on the planet to launch from.
Yes. In fact, that's true. So this was an interesting issue with the one that I just mentioned, that the FCC license was denied. And the reason why it's interesting is because they actually launched from India. They were on one of the Indian rockets. And so there was a significant question as to whether or not the FCC could even regulate a satellite that was an American satellite that was launched from India. And so it's not settled law right now. These are definitely questions that are being worked through. Yeah, come next month and talk to Charles.
I'll be here.
Thank you for your presentation. Can you tell us about your expectation about Nanosatellite in 2030?
I'm sorry, I didn't catch the last.
Can you tell us about your expectation of the Nanosatellite about 2030? I mean, I'm asking about the future of Nanosatellite.
For 2030?
Yeah, after 10 years, yeah.
In 10 years. It's really hard to predict what's going to happen in 2 years. So 10 years down the road, I will tell you that the space industry will look significantly different. And I think nanosatellites will have a significant role to play in that. And I can see a couple of things happening. One is that nanosatellites become as common as a desktop PC, in the sense that I want to put something in space and go down to my local satellite store, buy a satellite, put it on a spacecraft, which goes to the commercial space station and launches it from there. So, I mean, we're going to see more launch vehicles, we're going to see more traffic going into space, we're going to see a lot more activity in space. And so we're going to see more people having access to space. So I think that's one thing that you're going to see, is just more average people having access to space through small satellites. The other aspect of this, and I haven't really touched on this at all, is the opportunity for small satellites in deep space exploration. So I debated whether or not I should include this, and maybe I should have, but there is right now a mission on its way to Mars, which includes some small satellites, nanosatellites, and they are planning to do basically remote observation of Mars. And the advantage, of course, with the nanosatellites is they're much less expensive than a large satellite, so they can cover more territory with more satellites. So I think there's significant opportunity for deep space exploration, not just to Mars, but we're also going to see missions going to the asteroids as asteroid mining starts to become a thing. The companies that are doing asteroid mining are planning to build nanosatellites to do the prospecting. So we're going to see missions like that to prospect asteroids. And we could easily see missions going to Jupiter or Venus or other planets as well. Again, science missions for deep space exploration.
Thank you for the presentation. And I have a question that what happened in 2013? I just noticed when you give the presentation between the year 2013 and 2014, there is a huge growth in the commercial use for the nanosatellite. What happened that year?
Between 2013 and 2014? I'm not sure specifically what happened there, but I mean, it's been growth for the last 15 years. So that particular, that graph started in 2013. If you go back more than that, you'll see it's just sort of a trend which is increasing. So, I mean, in 2013, I'm not sure exactly what happened. In 2014, there was, again, a pad explosion of the Antares spacecraft, the Antares rocket, and that actually took out a bunch of small satellite missions. So, I mean, to a certain extent, it's just noise, right, in the graph. But the general trend is definitely upwards. Other questions? I appreciate everyone coming out tonight. I hope you found this informative. We certainly have the space for another hour, so you're welcome to hang out, socialize, and talk about space more. Thank you again.